Welcome back to another Timberwolf Tutoring video. In this video, we will be covering Extrema. We will first go over Extrema conceptually. Then, we will move on to 3 problems, all from this calculus textbook.
So let's jump right into our journey in Extrema. So to start off, we're going to look at this here graph. And this is a complicated 5th degree polynomial, but don't worry too much about that. We're just analyzing what it looks like, not anything about the actual function. So, looking at the properties of the graph, we can see that it's increasing over here, then right here it sort of levels off and starts decreasing, starts increasing again here, starts slowing down, but then increases up to infinity off here. So that's the properties of the graph. So now we know that, of course, but now what we have to do is we have to look at the actual features of this graph. And when we click on it, we can see all these points pop up, and we have like x-intercepts and y-intercepts, and these things called extremums. Or extrema, plural. So what are extrema? And it turns out these are the points where the function is either at its maximum on a short interval, or its minimum on a short interval. So you can see at this point right here, the function goes increasing up to the point, and is decreasing away from the point. That's because it doesn't go above this point ever. It doesn't decrease down to it, and it doesn't increase after it. So this is the maximum point on the value. And what this means is, since it's increasing on the left and decreasing on the right, then it's neither increasing or decreasing at this point. In other words, there's a horizontal tangent line to that point, and the derivative at that point will be equal to 0. Similarly, at this point down here, it's decreasing up to it and increasing after it, so the horizontal tangent line will again exist, and the derivative is still equal to 0. So now, how can we model this? Well, the point here, the tangent line, is not only at these 2 points, but you can draw a tangent line to any point in this graph. So let's do that now. This is a tangent line at x equals 8.5. And you can see that there's this little slider up here showing where x is. But let's watch what happens as the tangent line moves along the graph. You can see that the slope is very, very positive as it's moving along. And it's still positive now, but once we get to this extremum right here, and you can see we're almost there, it's suddenly going to switch from positive to negative. And right there, it's actually going to be horizontal. And as it approaches the other extremum, you can see it'll switch back to being vertical again. And I'm going to leave this animation playing. Go ahead and quickly watch it. So the other thing you can look at is, we want to see how the slope of this tangent line is changing over time. In other words, we want a graph of the derivative of this function. So we can calculate the derivative using the power rule several times. And so here's the graph of the derivative. This is a 4th degree polynomial, of course. I'm going to hide the original function. And we can see that this has its own extrema, but those aren't important. The important thing is that the derivative is equal to 0 at these 2 points here. One at 3.48 approximately, negative 3.48. And one at approximately negative 6.60. And what does it mean when the derivative is equal to 0? Well, in that case, it means it's our extrema here, or what's called critical points. And you can see that these x values perfectly line up with the thing we call extrema on our original function. So that's great. So now let's look at a different function. This one is x to the power of 2/3. And we can see, where do you think the extrema is here? Well, it looks obvious. It's at x equals 0, because that's the minimum value of this graph. But what's the derivative at that point? Well, as you probably already know, it's a sharp point, so the derivative won't exist. And when we graph this derivative, you can see that it has similar consequences. Watch what happens as it approaches 0. Currently it's at negative 2. And you can see as the tangent line moves closer to 0, this happens. Watch, it just suddenly jumps across the graph. And that means that at 0, at that exact value, the derivative will not exist. But that means that, in addition to the derivative being equal to 0, if the derivative doesn't exist, it's also a critical point. And critical points don't always have to be extrema. For instance, if your function follows this path, it goes here and then it turns horizontal but then starts increasing again, it will be a critical point, but not an extremum. So, it's a bit difficult to understand those without a picture, but I trust you can draw a picture yourself. And it's time to move on to some problems to understand extrema just a little bit better. Right, so now that you understand the conceptualization and how extrema work just a little bit better, it's time for some practice problems to really solidify the understanding. So let's jump right into it. And the first problem here will be this one. The order and transportation cost C of bottles of Pepsi is approximated by this function. C of x is equal to 1 over x plus x over x plus 3, where x is the order size of bottles of Pepsi in hundreds, and C is the cost in tens of thousands of dollars. Find all critical points on the interval 3, 6. In other words, find all points in this interval where the rate of change of C is either equal to 0 or doesn't exist. And you are allowed to use a calculator for this problem. So first, you might notice that this is also the same problem as the rule theorem video, and it's a continuation of that problem. So in that video, we proved that one critical point at least must exist on the interval. But in this video, we're actually going to find where that critical point is. So get ready for some algebra. So first off, how do you find critical points? Well, those are where the derivative is either equal to 0 or doesn't exist. So let's check what our f prime is first. Well, we can use the quotient rule, and we can also rewrite the first term 1 over x as x to negative 1. Feel free to rewind the video if you need to see the function again. And I will give you a bit of time to solve it. Go ahead and pause the video if you need it. And right, so now that you've had your time to think about it, the derivative of this function is equal to negative x to the negative 2 plus the fraction 3 over x plus 3 squared. So that's the derivative. Now we have to set it either equal to 0 or non-existent. So let's go ahead and do that. So first, setting equal to 0. That means that since you're adding a negative to a positive to be equal to 0, you want the positive plus the positive to be equal to 0, or them to be equal to each other. Because if x to the negative 2 is equal to 3 over x plus 3 squared, then when you add one plus the negative of the other, it'll just be 0 because the terms are the same. And so we get that equation there. And now we multiply both sides by x squared, do some fancy algebra in there. And I'm not going to explain in detail all the algebra because this is a calculus video and an algebra video. But feel free to pause the video and work through this yourself. And I'm not going to solve the rest of it. I'm going to leave it to you. But please pause the video here and solve for x. And remember, you can use your calculator on this. Right, okay. You had enough time to solve for it. If you need more, please pause the video. It's very important that you work through this yourself. The best way to learn calculus is by actually doing problems. You can never learn it just from watching someone else do it. But now that you've had your time, the answer is that the case where f of prime of x equals 0 is at x is approximately equal to 4.098. And the exact value is 3 root 3 plus 3 all over 2. So now we can set the derivative non-existent, and the values there are 0, because you can't take 0 to a negative power, and negative 3, because then you're dividing by 0 on the second term. But we can exclude both of these, because neither of them are within the interval 3, 6, and that's the only interval we're looking at on this problem. So now that we found all the critical points, we can accurately say that the only critical point on this interval is at x equals 4.098. So that's problem 1 for rule theorem, and now let's move on to problem 2.
Okay, so for the second problem, we have find where the function f of x is equal to x to the fifth minus 5x over 5 is increasing and decreasing. Apply the first derivative test to identify all relative extrema. So pause the video here if you'd like, and try to solve the problem by yourself. Okay, so the first thing we can do here is rewrite this equation. Instead of x to the fifth minus 5x divided by 5, we can split this into 2 and have x to the fifth divided by 5 minus 5x divided by 5. And we can do this because we know that all numbers in the numerator are individually divided by the number in the denominator. So once we rewrite it, we have x to the fifth divided by 5 minus 5x divided by 5. And it's much easier to take the derivative of this than the original function, as we'd have to use the quotient rule in the original function. And here we can just use the power rule. So let's find the derivative of this. We bring down the 5, subtract 1, and we have 5x to the fourth. Divided by 5 will just be x to the fourth. And then over here, 5x divided by 5 is just x. and the derivative of x is just 1. So we have x to the fourth minus 1 as the derivative. The next step will be finding the critical values. So to find the critical values, you either set the derivative equal to 0 or find the values in which the derivative does not exist. So when we set the derivative equal to 0, we get x to the fourth. Then we add 1 to both sides, so x to the fourth is equal to 1. Then we take the fourth root of both sides and get x is equal to plus or minus 1. So it's equal to both positive 1 and negative 1. And those are our critical points. And there are no values that we can plug into the derivative for having it not exist. So we don't have to worry about that in this problem. Next, we have to find the increasing and decreasing values. In order to do that, we already have the critical points. So we can plug in any number from negative infinity to negative 1. And if we plug it into the derivative, because we want to find out if it's increasing or decreasing, so we'll have the slope, then we will get a positive number or something greater than 0. So we know that if we plug in any number between negative infinity to negative 1, the function is increasing as they're all positive. So we have that as an increasing value. So that's one of the points. And then now let's do let's plug in some points from negative 1 to 1. And our test value can be 0. So if you plug in 0 here, we get negative 1. And all the numbers between negative 1 and 1 plugged in would result in a number less than 0, so decreasing. And then finally, we have the interval 1 to infinity. And if we plug in any number from 1 to infinity, not including 1, of course, then we'd get a number greater than 0. So we have an increasing. It's increasing. And a test would be 100. So now that we have those values, what does that mean? We want to find all the relative extrema. So by the first derivative test, we know that x is equal to 1 is a relative minimum, and x equals negative 1 is a relative maximum. And how do we know that? Because from negative infinity to negative 1, where it's increasing, and from negative 1 to 1, it's decreasing. So it goes and it's increasing, 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 and then decreasing. So at this point up here, negative 1, it goes from increasing to decreasing. So that's a maximum. Then from 1, it goes decreasing, 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 and takes a sharp turn to increasing. And so that point down there would be a relative minimum. So 1 would be a minimum. When x is equal to 1, it would be a minimum, and then x is negative 1 would be a maximum. And there you have it. You have the increasing and decreasing values, and you've applied the first derivative test, and you have all the relative extrema.
Right, so for our last problem for today, we have this one here. We have to find where the function f of x equals cosine squared of 2x, and we have to find on the interval 0 to 2 pi, and it's an open interval, so we don't have to care about the endpoints. And we need to find where it's increasing and decreasing, and then we have to apply the first derivative test to identify all the relative extrema. So step 1 is to figure out where the extrema are, and to do that we can take the derivative of this function. So to take the derivative here, you can use chain rule twice. I'd recommend pausing the video and solving this yourself. Alright, now that you have some time to solve it, pause the video. And here's the answer. It will be this. Negative 4 cosine 2x sine 2x. Or if you want to rephrase this, you can say it's also negative 2 times sine 4x, because this is just the double angle rule for sine. But that's not as important for now. So now what we're going to do is, to find extrema, we know that's when or critical points rather. We know that critical points are when the function is either equal to 0 or does not exist. The derivative anyway. So first we set it equal to 0. And this means that either cosine of 2x equals 0 or sine of 2x equals 0. And so using our unit circle, we can see this just must be one of the 4 points on the unit circle, because either x or y has to be 0. So we know that 2x equal to one of those points. And so this means that when we divide it by 2 and just get x, it can be any of those points plus the diagonal points in between them. So it's a multiple of pi over 4. And we can list out all the multiples of pi over 4 on the interval 0 to pi, excluding the endpoints. And we just get this list here. And we also know that this function will never not exist because there's nothing being divided by. So this is the entire problem. So now that we have all the critical numbers, what we have to do is figure out which of them are minimum, maximum, and neither. And we can do that by calculating the derivative on a test point on each of the intervals between them. We need to find one test point between the starting value 0 and pi over 4, one between pi over 4 and pi over 2, one between pi over 2 and 3 pi over 4, and in all the intervals we have to calculate the derivative of a point between them. And in doing this, we'll figure out, using the first derivative test, if any of these points are minimums or maximum, and also if the derivative is positive, it'll be increasing on an interval, and if it's negative, it'll be decreasing on the interval. So that'll be how to solve the problem. So I would recommend you go ahead and try that one on your own. And so, as a hint, I'm going to say that you probably want to test angles like pi over 6 and pi over 3. But I would recommend definitely solving this on your own. You're going to need the practice. And I wish you the best of luck. And I hope this video helped you understand Extrema a bit better. Peace out.
Thank you so much for watching our video. If you want to contact us, you can reach out to us on email at timberwolftutoring@gmail.com or on Instagram at Timberwolf Tutoring. Let us know if you have any questions about the topic covered in this video, or if you want to see a specific topic covered in the future. Be sure to subscribe and turn on notifications so you're not missing any of our latest videos. This is Aiden and the rest of the Timberwolf Tutoring team signing off until next time. Thank you again.